Hey everyone, Rob here from Rising Edge Industries, and we're going to do another quick take video to go over the burst mode functionality. And so this is a second of two run modes. There's one shot in the previous video we discussed, and now we'll talk a little bit about the burst mode capabilities of this, which is really a way to use a pre-trigger memory buffer, and the device automatically monitors all the incoming samples, and upon a sample value violation, switches from pre-trigger memory to post-trigger memory to give the customer a complete before and after picture of the event of interest. So we've got our usual test set up here. This is the unit we're going to be testing. See, it's been triggered, so we'll reset that and go over the configuration quick. And so we've got our input stimulus here, which are two 100 millivolt peak-to-peak out-of-phase sine waves offset by a positive 50 millivolts DC. So basically we have two out-of-phase sine waves coming in at 1 kilohertz here on channel 1. The rest of the channels aren't connected, and so this is just a simple test with some lab equipment here, mainly an ARB in the lab. So before we get started though, let's go over this timing diagram. So there's a pretty simple timing diagram that I think will illuminate most of this functionality. So turn off our webcam showing the units. Okay, so this is a simple timing diagram, and really all we're trying to show is what the internal data recorder engine is doing relative to different input stimulus and operational characteristics. So we'll read this from left to right. On the top there's the engine state here, which is, this is just the main internal data recorder digital engine, and that's basically a catch-all title to cover all the logic in the product. So you can see right now it's blinking. We've got our blinking LED. You can see earlier in the webcam screenshot, I'll bring that up again quick. You can see right here. So that means we're in idle mode when that's blinking. And so that's where we are here. We've just talked a little bit about the triggering mechanisms. There's three, and so see our triggering videos for more detail on that, or the documentation. We won't go over that in detail here. For burst mode, we'll just use the USB command since we're in a lab setup here, and we haven't connected up any discrete input triggering. But you've got one of these three will be your initial trigger for burst mode. And you can think of it as having two triggers. One trigger, the first one here, represented by this pulse, comes from one of these three inputs. And so in our case, the engine receives a USB command to start sampling, and that's all the trigger we need to provide. And so it's a two-step process, and we've denoted that here with basically two different states. So we've got pre-trigger buffering and a post-trigger data acquisition state. So both of these are acquiring data. They're both data acquisition states. So when we receive the trigger event, here we go from idle into operation, and we begin pre-trigger buffering, which means the data recorder is now running as configured, sampling data, and it's using basically a ring buffer or a circular buffer, looking for a threshold violation, which will come later in the timing diagram. So right now the engine is just looping through this 4 megabit pre-trigger buffer, which effectively gives you a 4 megabit history from the event of interest, which would be here. So it would be a data sample that is greater than the threshold programmed, and we can open this up along with the configuration tool here, just to be extra clear. So on the configuration tool, the threshold that we're referring to in this timing diagram is this option right here, threshold. And so this threshold is an ADC code between 0 and 4095 that's applied to a channel, 1, 2, 3, 4, or all channels. And so this is where the threshold here and our timing diagram is set, this threshold right here. When a data sample that is greater than this threshold, so we'll say if we had set this ADC code 2550, so if we get 2551, then we have our secondary trigger event that is automatic and internal to the device, and that's our event of interest, and that transitions us from our pre-trigger memory circular buffer over to our post-trigger memory here in this state, post-trigger acquisition. These both write in real time to both non-volatile memory spaces. So T sub P is the period of time we're writing to the circular buffer, and we could do that for a second, a minute, an hour, a day. And then post-trigger memory, just to elaborate, this is going to keep looping until a data sample violation occurs. So this is kind of a set and forget mode. If you know what to expect on your sensor, if you know what sensor output to expect, so differently, if you know what signal you want to capture on the input channels, then you can set this threshold and just let the unit run as long as needed. So this just keeps looping. When it gets the event, it transitions to post-trigger, and post-trigger doesn't loop. Post-trigger runs for a finite duration programmed in the user settings, and that's runtime here. So for example, if we use this configuration, 60 millisecond runtime, what would happen is we would be digitizing our input channels, checking all of those samples in real time to see if any of them violate our threshold preset. And once that occurs, in this example, 60 milliseconds, this T sub O is the post-trigger memory write period, is going to run for 60 milliseconds. Then we're going to stop here, acquisition done, go back to our idle mode, and keep in mind there's a small note here, do not trigger. So from the trigger event here, this rising edge, to the end of this red arrow, this dotted line, that is one burst mode data capture cycle in here. And so at this point, right here where the green arrow starts, acquisition done, we are no longer acquiring data, and we are in idle mode. But it's important to note that the device should not be re-triggered yet, and the device will not allow itself to be re-triggered. This is discussed in some of our detailed videos in our other playlist, but to touch on it quickly, to preserve data safety, to ensure the customer doesn't unintentionally erase data, once the recorder goes through a complete data run, it is not re-triggerable until an explicit command, this bottom line here, this is a data bus on the timing diagram, USB commands. So what you have to do is issue a reset and an erase, or an erase and reset. But it's critical that customers download their data file and verify them here in this step. After the data files are downloaded, you can erase your post-trigger memory space and reset the engine. It'll still be in idle mode, but what you will notice, and in the beginning of the video, we had two LEDs on. Now, since I've reset the unit when I launched the configuration application, the reset light, the third one over here, went off. But in the beginning that was on, and that's because the device had been triggered, ran, and has not been reset. So for completeness from a customer's perspective, I wanted to fill out this timing diagram in a little more detail, and you can see once you execute an erase command and you execute a reset command, now the device is ready to run, the memory space is clear, the idle mode now is ready to trigger, and you're good to go. So you're ready for next data capture. And so I just drew out one more short little cycle. But this is the main intent behind the burst mode operation. And it's really handy because it allows the data recorder to capture really high frequency events that a user couldn't capture, and it allows customers some freedom in that you don't have to know the run duration. This pre-trigger mode will run and run and run continuously until your event of interest is found, or if there is no threshold violation, if the input signal on one of the 4 input channels does not exceed the threshold, then you'll just see this thing running. You can hit the stop button. The data recorder will go back to idle mode, and you can reconfigure and interact with the device. You can rearm it and change some of the parameters, adjust the gains, change the threshold, and start a new data acquisition series, just like shown here. So there's also a blog post about this with a pretty good write-up and some good screenshots on our blog, so please check that out at our website. But now we'll do a quick demonstration just to show this in action. So keep in mind, we're going to do a configuration. We'll manually trigger the data recorder to start its burst mode operation with a USB command, and then after that we'll generate this violation by increasing the sine wave input on channel 1 that comes from our signal generator in our lab here. So we're going to induce this event threshold violation here. This event's induced with test equipment, since we're just spoofing a signal with sine waves, and we'll do a USB command to here, acquire data for a little while, point out the LED in operation, show that the engine transitions to a burst mode pre-trigger data acquisition buffering, and then we'll show that it finishes, it shows it's triggered, and then we'll look at the data file. So let's get started. So we're connected to the device, reset, we'll do erase command. Since we're only running for 60 milliseconds, we'll erase 1 meg of post-trigger memory. We're good there. So now we're ready to start. We've got everything set up. Our signals are 100 millivolt peak-to-peak out-of-phase sine waves are on and connected to channel 1. So we'll start. Oh, first, let me turn this back on so you can see we haven't started yet. I'll click the start button now, and now you can see the middle light is on, indicating the data recorder is busy. The third light is on, indicating it has been triggered, which is here. So right now we're in pre-trigger buffering. So we're in this state right now. You can tell that by the LEDs. So what we're going to do now is induce this violation on our input channel by just increasing the magnitude of our sine waves that are driving channel 1. And we can see that in our configuration readback from the data recorder, we're looking for a sample to violate 1675, so the ADC code 1675. Anything above that's a violation and will cause us to end pre-trigger data acquisition, capturing a 4 megabit history, transitioning to post-trigger for 60 milliseconds. Once that 60 milliseconds expires and that data block is in memory, then we'll be here, idle, acquisition done, and we'll download the data file and check it out. So now I'm going to just adjust the magnitude of our input signal, and because 60 milliseconds is so quick, you'll see that the LEDs change, indicating a data acquisition is finished. And so I'll push the button now, and you can see they have gone off. We're blinking back in idle state, and the triggered LED is illuminated, just letting the user know that before another data run is executed, you really need to get your data file erased and reset. So now we'll download our data file here. It's going to be in the root directory of our application under the serial number here. And so right now we're in this state, idle, do not trigger. We're getting our data file. And so now that we've got our data file, we'll look at it first just to make sure it looks okay. Let me move that over here. And so we'll run our data analysis tool. Move our console. Okay, we'll go in the root directory of the configuration application, go to download, serial number 20, voltage. Actually, we can look at the ADC code data right now. So we triggered at 1675. You can see we're looping through at 500,000 samples per second continuously while we were pointing out what state we were in, which is here. So this pre-trigger circular buffer state represents this data right here up to this ramp. And so when we have a sample that breaks our threshold of 1675, which is right up here, we transition to 60 milliseconds of post-trigger memory, and we get a resulting waveform that looks like this. So these, now if we can turn our webcam, our data recorder webcam off, we can make this bigger and zoom in to some of this information here. So we'll look at our waveform. There's our sine waves, and we'll look at our transition event. Okay, and then we can also say 1650, so we can also look maybe a little closer here, put our cursors on, see if we can find our threshold violation. So we've got 1632, it should be as simple as 1666, go up here. So I've got 1670. We may need to zoom in a little bit more. And so we'll look at these. Turn our zoom off, grab our cursor. Okay, so we're at the top. So 1672, 73. So one of these peaks, and we may have to go a little bit, 74, so we have to go over a little bit more. So let's do that. Let's go over here. What is this? So 1675, 1677. So that is probably the peak, if not one of these right around here, is probably the peak that triggered us. So you can see our Y value is 1678. So let's look at our timing diagram again and minimize that. And so we can see that event here. Pull up our data utility. This peak here gives us a sample value that's over our threshold, and this is most likely where this event occurred here. This was our 60 millisecond run duration of post-trigger memory, and then we are now in idle mode, but not ready for another trigger. So we've downloaded our data file. It looks good. The next thing we want to do is erase the memory. So we'll do a quick memory erase. It'll just be 1 meg. See memory erasing, there's a quick take on that. We did 2 sectors. This is covered in detail on that video. Won't go over that here because this video will just be too long. And so now I'll turn the data recorder webcam on. You can still see the LED indication letting you know clearly this hasn't been reset. The data engine's not ready to be rerun. Even though memory's clear, you have to do both of these things. So we just erased the memory. So in our timing diagram, here, we just did this, issued a memory erase command, erase the meg. Now we're going to reset it. When we click the reset button, you'll see right here, this LED is going to shut off, letting you know that it's, there you go. So now you can see it's off. The blinking idle state's the only LED indication on now. And the data recorder's good to go, ready to run. And so move our magnitude down on our input so it doesn't trigger too fast, and issue our start command. And now we're back up and running. And we're back up and running in this mode right here, the very beginning. Make sure I can display this. So right here, we're running through our circular buffer at our max data rate, 500K on channel 1, waiting for threshold violation. And right now we're running off USB power. It's plugged in over USB. And the orange light we usually have on in this series is off because the data recorder is actually fully charged for this video. So this covers quickly how to the design intention behind burst mode, some of the benefits we're trying to afford to customers, and then a quick demonstration here just to walk through the steps to get this configured and operational. And it's pretty simple. You just select from one of two run modes, burst mode, configure your threshold value and channel to monitor, or all channels, and that's it. Those are the only two special configuration steps. Two clicks to go from one-shot mode to burst mode. Everything else is the same. This works with all the gain. You can set up, if you wanted to do 6 seconds, 6,000 milliseconds, or more. You could do much more than that. All of the normal configuration knobs and tools apply to burst mode. So there's nothing special from a configuration perspective other than the threshold and which channel to monitor. So thanks for watching this, and if you have any questions, you contact us through our website or support at Rising Edge Industries, and we'll see you on the next video.